Yeah, so welcome everyone. I'm very happy that Remo Burn was able to visit us after attending the Exoplanet 4 meeting in Las Vegas. That you made the additional effort to deviate your travels and come over for a few days. Remo is an expert in planet formation, and in particular, he studies M-dwarf systems, not only, but he has a special interest in those and also in the connection of the properties of protoplanetary disks and how this affects the exoplanet population. So he's an exoplanet population synthesis guy, if I may say so. And Remo did his PhD at the University of Bern in Switzerland. And after that, he joined the Max Planck Institute for Astronomy in Heidelberg as a postdoc, where he's based right now. And today he will talk and tell us a little bit about, exactly these connections between disk measurements and planet formation, or as far as that works, right? We were very curious to hear about that, and yeah, please take it away, Remo.
Thank you. Thanks very much for inviting me. And yes, I'm not sure how if my project is already advanced far enough to really tell us about planet formation. Maybe a bit already, but we'll come to that in the end. Yes, I'm very grateful for the Swiss National Science Foundation funding, which funded my last 1.5 years. My first postdoc at Max Planck now. But the logos I put on the top are all the three. So I'm still having a bit of content from the University of Bern. And this is what I start with, basically, my work on planet formation, population synthesis for low-mass stars. And then I looked at dust entrainment. So maybe that's something new for some people in photoevaporative winds. And in the end, I come to what I promised in the abstract. I will talk about what I try, or how I try to get information from the disk observations for our planet formation models. So in the big picture, where are we? We start with the protoplanetary disks. In there's dust and pebbles which grow into planetesimals, and just also I use this slide also to use or to introduce my nomenclature. Planetesimals for me go from 100 meters up to 100 kilometers, and then I usually talk about embryos. Well, in my mind, embryos are round and planetesimals have any kind of shape. That's my distinction. Then the embryos, they can collide with each other or continue growing by pebble or planetesimal accretion. And if they do that quickly enough and become massive enough to attract a lot of gas, which then contracts, which leads to more gas accretion, this runaway gas accretion process, you get a giant planet. If they remain small because there was not enough growth, they collide with each other and become something like a terrestrial planet. And this step from embryos to terrestrial planets is what we improved on the most, I would say, compared to old population synthesis studies. They're almost 15 years ago, where they published 12 years ago, to what we published last year. It's really that we include now more n-body particles, and we think we have much more reliable results also for small planets, because in the past, the population synthesis work in Bern was mainly a giant planet population synthesis. And now we think we also have reliable results for terrestrial planets, which also makes it natural to then look at M-dwarfs, because there you expect to have more terrestrial planets and less giant planets. So you need a model which can cover that. And of course, one of the people on my slide is here. You know him very well. Alexandre Emsenhuber works a lot on this model, together with Jan Alibert on the bottom right here, and Christophe Mordassini in Bern already. So I will not do a full review of what he did in this 2021 paper series. I I think you might have heard from Martin already. He recently gave Origin seminar talk. I just very briefly repeat the philosophy behind this kind of model is that you use 1D models for all relevant processes. Is the goal to have all relevant processes that happen relevant for planet formation that happen in a protoplanetary disk. This includes a 1D disk structure and an envelope structure, growth by accretion of planetesimals. Here we don't track the individual planetesimals with an n-body, but use a statistical model of planetesimal accretion. We use prescriptions for migration, and the n-body interactions, they are easy enough to really do, at least between the embryos, not between the planetesimals. So if you have up to 100 bodies, it's still reasonably fast to be able to compute thousands of those systems, because only then you can do the statistical comparison with exoplanetary demographics. So that's the idea, that we want to have a model that's quick enough to do it statistically. And then what happens is something like on this screen, mass semi-major axis diagram. You saw a lot of accretion and growth. Wherever two planets collide, I put an X, and now the links between the planets are resonant chains that emerge once the planets grow and migrate inwards. So they migrate usually from outwards in. And we had now also a few circles appear. This is the TRAPPIST-1 planet as we thought about it on 2019 by Sam Grimm. Now the mass has already changed a bit. And something I would like to highlight today, because I was at Exoplanets 4, where people talked a lot about compositions of super Earths, actually, is that we also predict a nice core mass fraction is plotted here. So we predict how much ice a planet would have accreted based on where it accreted the planetesimals, so from outside or inside the ice line. The most important one is hydrogen, water, of course, but we also include other ices, and we have compositions for them. And what we predict is usually that, well, of course, the rocky ones are closer to the star than the icy ones, but there's also a mass gradient, as you will see later on. So what do we put in as parameters for those models, or what did we put in last time we completed this exercise? Is 50 embryos, 5 different stellar masses, so we did a grid. And the embryo starts with a moon mass about, and alpha, I will come back to that a lot. The viscous alpha parameter is 2 × 10⁻�3, so it's a measure of viscosity, and if you're in the field, you know that this is always highly debated and unknown what exactly it would be. Similar for the planetesimal size, we use very small planetesimals, which helps to make the timescales fast enough, and we have to be honest about that. This is one of the tuned parameters. We wouldn't be able to reproduce the exoplanet's demographics with 100-kilometer planetesimals, right? But within thousands or 2 kilometers, 3 kilometers could still be fine, actually. And then what comes out is those 5 populations here. So now each panel here at the bottom includes 1,000 systems. So up to, initially those were 50,000 embryos per stellar mass. So it's quite a significant computational effort we made here. And one thing I would like to highlight today, there's much more in the paper from last year. But one thing is that really we now have blue color on the top and green, yellowish color at the bottom. And this means the rocky ones are usually of a lower mass than the icy ones, and we would always predict a lot of icy planets, at least also for the low stellar masses. Maybe we zoom in one of them. Oh, okay, we don't zoom in today. You can, yeah. I think the only thing that you might barely see now is that there's the giant planet GJ3512b is up here, right there. There it is. It's really not reproduced, so we would predict no giant planets to form around the 0.1 solar mass star. But the rest of the small planets, they are more or less where we would expect them.
The lower right panel, do you think we can remove it? Maybe from the motion.
Maybe from. And I also highlight here in the boxes are the temperate zone limits from
No, that's okay.
From Koparapu. And it moves quite a bit relative to our population. If you see the around the solar mass star, it's much further out relative to the orbital period actually, which gives you different compositional predictions and different mass distributions in your temperate zone. So it's quite different planets from their formation perspective. But to do those, to show those results, and I inverted here the order of my slides. We had to assume some initial disk conditions, and that's very important because basically what you put into the model is also what you get out. So we fixed the that's not
missing.
Yeah. Oh, this one shows up. Okay. So one thing we assumed is that the disk lifetime around smaller stars. So we had to assume initial disk conditions and scale them with stellar mass. That's what I had to do for this project. And for the lifetime, there is a trend with mass that was found that the more massive the star, the shorter the disk lifetime, but that is actually from stars much more massive than one solar mass. So there's no confirmed trend for going from one solar mass to lower masses. So we didn't really know, so we just took the same disk lifetimes. So about 3 million years. The inner radius is quite important for the population because it's basically the migration trap at the end. So this is where your innermost planet will stop at some point during its formation. And we put that at the co-rotation radius where the theoretical picture is that you have magnetic field lines orbiting at the same speed as your material, being able to lift up your ionized particles, and this gives you a natural inner edge for the disk. So we went into the literature and found rotation rates of T Tauri stars. They were measured. T Tauri is, of course, the ones that still have a disk. So we didn't go for the old ones where there's then again a trend with stellar mass, but the youngest ones where rotation rates were measured didn't show any trend with stellar mass. So I also took the same orbital period of the inner edge for all my stellar masses without scaling. And the distribution of those inner periods you can see here, it's more or less at 4 days is the peak. And it's a bit closer in than some other works, but more or less the same ballpark. And then the most important one you can partially see here now. This is a histogram of dust gas masses for class 0 and class 1 disks as measured by the Tikhonov. So by class 0 and class 1, because it's now known that the class 2 disks, so even older disks, they don't contain enough material for planets to grow. And this is why for this project, we just went for class 1 and said, this is our initial condition. And we can maybe discuss with Alexandre a bit more, but he also has a project ongoing where he compares to those class 1 masses. But basically we took those mass estimates and now of course the plot is also up. I don't know what's happening. I think that's when you don't use PowerPoint was the LibreOffice. But at least some parts you can see, the paper from Ilaria and also from Megan Anstel 1 year later, they showed that this masses scale with stellar mass in the class 2 measurements. And how it was interpreted there in those works is that it's an evolutionary trend because there's an age dependency that lines up, the slope lines up nicely with, increases nicely with estimated ages of those clusters. And if you go back in time and want something for time 0, it's more or less the scaling is more or less consistent again with the linear scaling at time 0. And then we took that and assumed that it's a purely evolutionary trend. I mean, it could be evolutionary and intrinsic initially. So, but we went with linear scaling, and those are so important because we only had one chance basically, because our model is fast enough to do 1,000 systems around 5 different stellar masses, but not fast enough to then do on top of that another parameter study with different scalings and different parameters. That's where we're a bit too slow if we want to have those n-body particles, those 50 n-body particles.
Remo, would you like to allow a question by
Sure, that's actually my conclusions for the first population synthesis part, and maybe also the best time for questions. Yes.
Andrew.
Okay, Andrew, go ahead.
Yeah. So I guess first a clarification, and then I guess the science question. It was, I understand there's an issue with the slides there. So what's the range of disk masses that you're including in the models?
So here,
yeah,
that's dust to gas masses, and they're basically from you see it here. The blue line is from -2, 10 to the -2 to 10 to the -1 solar masses. That's more or less the order of magnitude we are, and so I think the mean is at something like.
Okay. So I guess I was confused. I thought a minimum mass solar nebula is around 10 to the -2, usually maybe a little bigger. I thought people had said, and that you just repeated, that the observations tended to be much less than that, whereas here everything looks like it's, most data looks like it's above.
Yes.
Is this different than standard, or?
I think now, well, when we looked at it, and we did that in 2019, this was the only estimate of class 0 and class 1 disk masses. And the many results for class 2 disk masses showed that it tended to be too little in class 2 disks to grow. So there's a paper on that by Carlo Manara with Morbidelli. And basically, from that, we knew it will not work. So we went for the earlier things where you also have larger uncertainties in those class 1 disks. They for example, they cannot measure the stellar mass precisely. So we assumed that this distribution here that they measured is for 1 solar mass stars. But now this was Orion, Tikhonets et al. They looked at Orion, I think. And now for different clusters, actually, they found quite a bit lower masses again. And so if we did it in 2022, we would, I think, go for a bit, something in between, a bit lower than that.
I think I can comment on the fact that so what is measured is the flux, and when you convert it to a disk mass,
yes,
there is a big uncertainty. So an order of magnitude is quite within.
Yes.
Now, I don't know if it's, I don't want to take all the time, but I also wanted to, maybe we should talk more about this later, but ask about the initial planetesimal sizes. That's a bit smaller than I think, what many people consider. And I'm curious if these models could, say, reproduce the asteroid or Kuiper belt, where people have argued that larger initial planetesimal masses are needed.
Yes, when we went through, well, I'm not an expert on the Kuiper belt or the solar system, but when we went through the literature, we found a bit both, right? For the asteroid belt, I think it was would be better to have a big one, big initial mass. But then there is also occultations that were measured from the Kuiper belt, where the occultation, the object is just small. And
I'm not sure you should be using the plural there. I think there is one very contentious occultation.
I think it's two now, but yeah, you're right. We argue a bit in the papers that it could be still with the small ones, but of course the big elephant in the room is then the planetesimal formation theory, which predicts that they should be large. So that's it's an issue still. I wouldn't say it's
even I would say the observations matter more than the theory, though. So
yes, yeah. So from observations, I think there's also Hilke Schlichting and people at UCLA. They think that actually you need to start small to reproduce the Kuiper belt. Because of the collisional timescales would be otherwise too large to have a distribution. But for the asteroid belt, I think you're right that most evidence points towards small.
Isn't there also
large initial planetism?
Isn't there also like the cratering record on Pluto? So that's
the impact craters on Charon, I think.
Yeah.
There was also discussion there that initially they thought it's big ones, but then the distribution should be dominated by the large planetesimals. But then I think now publications appeared where they put that a bit into perspective by evolutionary effects on the surface, and so I don't think there's a final answer.
So in your n-body simulation, how do you treat the mass radius relation of the planetesimal when you collide and grow? Do you assume like a constant density?
Yes.
So they're not. So the planetesimals are not in the n-body.
But still, the density matters for the gas track. Yeah. So the excitation and the inclination damping, we assume that it's two constant densities, one outside the ice line and one inside. Constant densities.
Then whether it collide or not, it depends on the size of the planetesimal? You say the planetesimal itself is not in the n-body.
So it's mostly dominated by the radius of the protoplanet. Of like the collision, that's the sum of the radii, and so like 300 meters compared to like 1,000 kilometers will not change that in the radius itself. What changes, what's important in planetesimal size, is also the number of planetesimals for a given mass. So you set the mass, and so of course the smaller the planetesimal, the more you have. So that's one thing, and then there is also all the dynamical states that changes with the different sizes. Also the number about if you have like the dynamical friction, that you have more. So the more you have, the less the less excited they get.
So it's the size of the planetesimal. The main why we talk about that. The main reason is that they are the smaller they are, the more damped they are. This is linked to the density. That's true. So the physical density of the planetesimals. Yeah. I think my take on, or my conclusions on the population synthesis work I did was or what I want to highlight today is that there's this compositional trend that you have. You saw the blue colors above the rocky ones. So the ice-rich, we also predict ice-rich super-Earths, and this is my big news from Exoplanets 4 that at least what's related to me is that there were like 3 talks talking about potentially super-Earths are water-rich. I mean, super-Earths, actually they would be what we used to call the mini Neptunes, so the ones above the radius valley, that they could be icy planets, and some are inconsistent now with having a hydrogen helium atmosphere, and also the talk by Rafa Luque was really interesting, that around M dwarfs he showed that where we have the best constraints, right, that if you just improve on the mass radius measurements, you line up the observed planets basically either on the rocky pure rock or on the 50% ice, 50% rock line, and they're like almost without scatter. If so, the whole scatter that was there was just that's his take, was just due to measurement errors. And if you improve on the errors, you see those two lines emerging, and that would mean that you would expect much more scatter if it was hydrogen helium plus rock, because then you can just shoot up in radius with a tiny amount of hydrogen helium. And also there's this paper by Julia Venturini, which talks about that in with respect to the valley, to the radius valley, that you can form a radius valley by just taking icy super Earths and rocky to be above and below. But that's what I found very interesting. And what we can do with the populations is really we can look at a lot of parameter ranges, and what I just want to mention here, that everybody who is interested in one trend, let's say metallicity and stellar mass and how many super Earths and cold Jupiters are then in each system, or whatever relation you want, you can also look it up on days.unig.ch, or you can ask us. We have the time to look up a relation for anybody who's interested in our data, but we don't have the time to write a paper for each dimension of parameters that one could explore, right? We don't always know what's the most interesting one, and so we do those big papers where then one sentence is maybe about the relation you would be interested in, but it's hard to find. And but please ask us about if we learn something either way, either it's in the population or then the relation that's interesting, or then it's nice we predicted it, or it's not there and then we learn from it. So it's really in both cases we are very happy to collaborate. And the initial conditions are very important, and if there's no other questions, I move to the second half. That's why I now also started working closer to the disk data, and so it's basically about those two arrows which were not there before here. Oliver Völkel in Heidelberg worked on that, and I use also his model, and I add this additional arrow that actually not all the dust and the pebbles, but we knew that a part also goes into the star, but it could also be entrained in photoevaporative winds, or in principle in any kind of disk winds. So this just means the wind carries with it part of the dust, or what's the fraction that it carries with it? That's the question. And let's go on to that first. So the question is, does the dust just follow the photoevaporated gas? And the story from my side was that I used those models as they were written, added photoevaporation to what Oliver Völkel included. So he included dust growth and evolution. And then when the gas was gone in my models, there was just dust left over. And then the question is this physical, or are we missing something? So I looked into the literature, found a paper from the Clark group, and they entrained a lot of mass in those winds. So they found that at least for externally driven winds, you tend to remove a lot of the dust that is there. And they also followed up, the same group, on this results, and basically for internal photoevaporation, it might be also quite a significant amount, but not as much. there the physics is you would assume that dust would settle to the midplane. So if mass is removed from the topmost layer, at least for the bulk mass, there's not much there. But what they showed with the 1D vertical 1D model is that you can actually, if you remove mass on the top, the disk expands again, and then you can carry in vertically advect the smallest dust back to the top. And if you look at that on a size of the grain versus semi-major axis or distance to the star plane, you can see. So I would like to draw your attention to this dashed dotted line and the thin line, gray line, and the green area covers from a minimum size up to what the model predicts is the maximum size. So in here, your fragmentation dominated, and then there's then at the outer edge your drift dominated, and out here dust didn't have the time to grow yet in this case. So that's an early snapshot. And there, basically the drift limit is much higher. So you could say pebbles of a centimeter in size can form there. And only the lowest months, like right where we put the limit would, so 10 to the minus 5 centimeters would be subject to this vertical advection and be removed. So very little, you expect very little mass to be entrained in the internal photoevaporation. But I come back to that because we have to fix a few parameters for if we want to study that. And my nominal, what I show here, my nominal X-ray luminosity is 10 to the 29 ergs per second. So maybe that's on the lower end on what you would expect. So this is a 1 solar mass star and basically a few hopefully reasonable assumptions about the relevant parameters here. And then we can not just plot this one plot, but we coded those processes, and now we can evolve the disk and see how much dust is actually removed. And it's in the nominal case, it's a few Earth masses. But for some parameters, we suddenly get much more. For example, if the dust, if the fragmentation velocity of the dust, so if the dust is more brittle, so that dotted line up here is for a fragmentation velocity of 1 meter per second instead of 10, and then all your dust remains small, and that's why you have much more small mass which can be removed. And how it's removed in those simulations is usually by external photoevaporation. If we vary that, this is the green dotted line. So if we would reduce the external the field strength of the external photoevaporation, you can reduce it quite a bit to below an Earth mass. And you see that varying the X-ray luminosity in this case didn't matter much. The red lines they're still close to the nominal ones. But if we reduce the external photoevaporation before and vary the X-ray, so if we go to a low value as you would expect maybe in Lupus or Taurus, and most of those star forming regions that we see today have actually no big O star in there, so you have a weak field. So you would basically turn off external evaporation. And what I show here is that if you then have a significant X-ray luminosity, you can still entrain the dust, a lot of dust. So basically, again, a few Earth masses. And what I skipped here is maybe the most interesting case, but it's always it's the viscous alpha. It changes so many things in the disk that it's always hard to interpret. Here, the interpretation is that, or what I checked is that actually with a high alpha, you are in a similar state as with the low fragmentation velocity, because the collisions between the dust are so strong that the dust cannot grow, and then your fragmentation dominated almost everywhere in the disk, and your dust will basically be there longer for photoevaporation to remove it. That's the main effect. So with this little excursion to dust entrainment, it can be significant. It can remove quite a bit of the dust mass, and especially so if some process keeps the dust small, then more is entrained, and you remove that, and it was kind of a necessary thing to look at first before I can come back and really compare dust models with dust evolution to the observations. I think it was really required to look at that first. But now we can do what we actually wanted to do, because planet population synthesis also naturally produces disk population synthesis. For each disk that you modeled, you would also get a disk output, right? And that's what was used once. So this is by the paper by Carlo Manara, where he collaborated with people in Bern. But what they had to do back then, 3 years ago, was to plot just mass accretion rates versus disk mass. And this was exactly Ilaria's comment from before. Here, they used just disk masses, gas disk masses, the modeled ones, versus gas disk masses multiplied by 1%. And then you get, this is what is plotted here. And this is really not, so there's the dust evolution and growth and drift and all these processes. And second, there is exactly that the dust disk mass is not a direct observable, but the flux. Other things one could do would be the disk radii, the profiles one could look at, or different wavelengths, or even the slope in wavelengths. But I didn't yet have time to come to those. But what I did is I improved on giving real disk observables with our model, instead of having to somehow guess relations. So there's also a guess in the accretion rates, namely the inner radius here. So an accretion rate is usually calculated from a luminosity. So if we want to model luminosities, we have to take our accretion rate and basically calculate the energy that is released from the gravitational potential when it falls into the star. And there it's really key to know from where it falls into the star. So that's kind of an upper limit. This assumes that you can see all this luminosity, but even before that, for this upper limit, you need to know from where it falls in. And we actually model that. We have an inner radius of the disk. So I took our inner disk edges that I showed before, around 4 days, to get the accretion luminosity. The stellar mass, there we just use the same stellar evolution models. That's hopefully okay. And the millimeter flux, there we now do the dust evolution, and we follow the Birnstiel et al. D-sharp paper, where they show in detail how you can calculate a millimeter flux out of your dust mass. So that's hopefully much better. What we now also introduce when we want to do a kind of a retrieval is that things scale with disk mass. So I introduced 3 additional exponents. The goal is, what I promised in the abstract, is to retrieve initial conditions of those disks. And so the question is really, can we, with those great class 2 measurements, can we learn something about what we have to put into our model for the initial conditions? Because we know now that this is just snapshot, one stage after significant evolution, what is measured there. And we have 3 papers in the pipeline, Alexander and I mainly talk now, for the rest, I talk about my 3rd paper, but there's also a more classical approach where we do a parameter variations and see which parameters go into the right direction. But there's actually 15 parameters, and this makes this exercise already quite hard. That's why we also want to do a Bayesian retrieval, basically based on our models. And there's a significant drawback, is that it takes a bit of time to calculate the model. So it's maybe 10 minutes to sometimes 24 hours, depends a bit how steep the gradients in the disk are that suddenly emerge. So this is without planets, just the disk and the dust. And therefore we cannot MCMC over with the real physical model. We put the circuit model in between, and that's a neural net. Maybe you can ask Alexandre about the details. This will be in his paper. And I used this neural net basically that was fitted to the physical model to then draw my few millions of MCMC sample, which would not be possible at all with the physical model directly. And what I feed as observational input is from the Manara PP7 review. It's now on the archive. And I took the lupus, chameleon 1 and 2 data only because that, for now, I will maybe go further, but they're more or less consistent with an age of 2 million years. So I took a snapshot of my models at 2 million years. And then before the retrieval, it looks something like that. You have the observations, accretion luminosity versus millimeter flux plane, and the simulations are all over the place, but not at very high accretion luminosities. And I explained to you before, we already kind of calculate the maximum accretion luminosity, so that's quite a challenging thing to go up there. But for the bulk of the observations, we expect to be able to find parameters which would match them. Even though there's like a bimodal shape here, this is from this fragmentation velocity, and this basically depends on fragmentation velocity divided by alpha, I think velocity squared by alpha. This is basically telling you what is the Stokes number of your particle, and if this fraction always remains small, then you tend to have dust that doesn't drift, and if you go high, then you have drifting particles, and the drifting particles really give you a fast 100 kilo-year evolution, and then it all moves to this second blob on the left for the low luminosities. And the observations are right between, so we don't really know what happens, but most people expect that particles would drift to some degree. So now we have to construct an MCMC. I did that following basically the Kelly paper, where you can also include sensor data, meaning upper limits for your data points. It's a bit more complicated, but not impossible. I have to admit, one caveat is that if you want to use a parameter as a variable, so basically I used the stellar mass as a variable. So there, if you have an error there, it gets terribly that's your X value and it gets terribly complicated to construct the likelihood with errors in variable. And I assumed that the stellar masses are precise, exact, the ones from the observations. But that's technical. Yeah, basically, from a technical side, it would become much more complicated otherwise. And Carlo Manara didn't provide error bars on the stellar masses in his table, so I kind of had no other choice. But for the rest, I hopefully include all the data, meaning I have the same sample that I used for the class 2 measurements, which gives you then what I retrieve should then be the mean of really the whole cluster, and not just the mean of a sample where you can observe it very nicely. That's why I have to include the upper limits, right? Otherwise, you get a mean which is biased again. But there, hopefully, it's less biased. And I use, in some cases, I use priors in the MCMC for the period, for the dust to gas ratio, and also for the inclination. Maybe I can come back to the inclinations later. But what I then get is basically my MCMC samples over parameters and tries to find something that matches the observations, and that's the histogram in the back here. On top is the data, again on accretion luminosity versus flux plane. And this is, of course, much better than the huge blobs that you saw before. So the MCMC really goes and samples where we think it should go. But of course, this is still output from the surrogate model. So the thing we put in between this neural net, right? Just to make sure. And we also can plot that as a function of the stellar mass. So at the bottom here, stellar mass versus millimeter luminosity. You can see that the observed fluxes have quite a spread, but we are somewhere more or less in the middle. And I have kind of one distribution per stellar mass. This is because I use the stellar mass as a variable, as I said before. The spread is, so what I show here as quantiles is the spread that we have due to the physical parameters. I additionally in the MCMC add an intrinsic spread, which basically moves, which then gives you an estimate on how much the scatter, how big the scatter is. But I don't plot this additional scatter. So this is kind of, it should be in the mean and the uncertainty of the mean that we have from this retrieval. The same one can do in the accretion luminosities, and I hope I convinced you that we go to the right parameter space. So now we really want to look what parameters are then actually retrieved. So it's this 15-dimensional thing here, which is hopefully now it works with the zoom ins. Yes, here it would be quite happy if we couldn't look at them in detail. So that's the top left one. I think maybe the most fundamental one is really the disk mass. And now I get something again, which is about 10 to the minus 1 of the solar mass, of the stellar mass in this case. Because actually the scaling of disk mass with stellar mass, it's down at the bottom, people in the room can barely see it, but it's the exponent of, so if it was linear, it would be 1, and I think it's still consistent. What I find in this set is still consistent with 1. The scaling could be something like 1, but a bit steeper. So maybe it's as I mentioned before, the observed trend in disk masses with stellar masses may be partially intrinsic and partially an evolutionary effect. But at least it doesn't go in the other direction, which I think is good. We also have an estimate on what could be alpha. It's 10 to the minus 4 is what the thing here tells me. So then one would think, well, with 10 to the minus 4, how do we get those high accretion rates, right? I mean, we don't even, not even with the most optimistic ones, we get a high enough accretion rate. So how can, with such a low alpha, how can we get the accretion rates or the accretion luminosities? And the model just found a trick to do that. It goes to very, very low outer edges of the disk. So you can basically say it wants me to dump all the mass already almost on top of the star, and then you don't need a high alpha to accrete it. You don't need a lot of viscosity then. So this is what this model is telling me. Well, of course, one repeats this all the time. I added variables and did all kind of things. So I'm not finished. This is still preliminary. But I think I'm now at the stage where I can tell you it was always trying to go to those small disks, and this is just because of the accretion luminosities. If I would just feed in millimeter fluxes, it would not do that, right? It would not give such a tight constraint and want me to go to very small outer edges. But that's due to that's the model solution to this problem that you have high accretion luminosities. And there, of course, there's also an exponent there, again, consistent with linear. And then if we look at the flux part of the millimeter flux part, or the dust part, I introduced a parameter zeta here in this set of simulations, and this is a fudge factor I put in front of the radial drift velocity. So this is really not very physical, but my idea behind that, or our idea, Alexandre, was that you can then model or like mimic that there's structures in the disk and not all the dust would just immediately drift onto the star if you have pressure bumps. So it's and we know that there are structures in the disk. So this is our way of without actually modeling the structures, which will give you infinite number of parameters if you would want to do that. It's a kind of what is the effect of the structures on the radial drift. That's our interpretation, and the model favors very low values there, and so kind of reducing the flux by a lot to with this set, it's then on a comparable time scale to the disk lifetime. The whole radial drift would then be at about the same time scale. So basically shutting off radial drift. And the inclinations, if I have time, I can talk about the inclinations of the disks. So this is really the physical inclination of the disk with respect to the observer, and there it tells me it's mostly edge-on disks. So I didn't really want that. So you see the blue line is my prior I put in. I tried to push the model a bit into the direction that, yeah, it's more likely to have edge-on disks, because that's just geometry. Bayesian is less likely, but I didn't want the model to retrieve this. So I should in the next iteration of this thing, I will fix the inclination to the mean value that you would expect, and then it will not just go to the very edge on disks, which is, I think, not a likely thing that in lupus, chameleon 1, chameleon 2 disks are likely more oriented towards us. That would be really unexpected. The reason why I did that is a bit here. If you look at plot inclination as a function, or the flux that you get for different inclinations, it's actually neither optically. It's, of course, the disk is neither optically thin nor optically thick. If you look at it at an angle, there you have an optically thick part and an optically thin part. And when people infer disk masses from the observations, they usually, I think they usually take the disk as face on even. But even if you try to do it a bit better and somehow sample over the inclinations, you would still not get it. You would then still have to assume something for the optically thick part. And here we can really, the model tells us where it's optically thin and where it's optically thick as a function of the angle, so we can do it properly. And properly means our results are close to the Radii results I showed for a few varied disk angles. And what happens is, as a function of time, as the disk thins out, you get closer and closer to the red line. So the red line would just be assuming that the disk is optically thin, even if you look through it back edge on. So with that, I can wrap up. Hopefully, there was a lot of things where I'm not very sure that it's an ongoing project, but I think right now we can already say that large disk masses is what is favored to reproduce the observations, small outer radii and low alphas. And somehow you need to then, with this set that reproduces the accretion luminosities, you somehow have to make the dust remain so long in the disk. You not just remove it by drift or remove it due to entrainment. But the real physics might be the substructures, that's my guess, but maybe there's some other effect. And the scalings with the stellar mass were more or less consistent with linear. in the future, I need to fix those inclinations. I also want to then use the physical model now finally to forward model once with the final parameters we got to really make sure that we didn't do something wrong when we in the step of training the neural net, right? Maybe the neural net did something wrong, but I trust my physical model more and want to pipe through those retrieved parameters at least once. So this is something to do. And also one could go for different clusters, different ages, maybe also as a function, well, age as a variable to have one super population like of all the class 2 measurements. And if it's true that the disks are really small initially, and that's not just my idea, but also star formation, people, when they include magnetic fields, actually most of the mass falls close to the star. And maybe that's the real physics, which we don't have in the model, but maybe that's why the model, it favors things that start with a very compact, massive disk, but that's actually a measure of where the mass should go through, like fall close to the star and then viscously spread. And this idea is also now arriving in the planet formation community. So Tim Lichtenberg wrote a paper basically saying that planetesimals are that form in such a scenario are more consistent with the solar system, and Morbidelli now goes in the same direction with his recent paper. And maybe I'm not the only person, but for me it was data driven, so I can say data tells me disks are small. But, yeah, that's really the big thing that planet formation people have to think about. How then planets form in this setting. And with that, I take questions, and thank you all for your attention.
I have 2 questions. So the first one on the disk radii. So you said, when you say you started the disk radius 4AU, this is the gas disk radius, I guess, and the gas and the dust are the same at the beginning,
Exactly.
Right? Okay. So then after 1 million years or 2 million years with an alpha of 10 to the -4, how large is your disk? Because we do have observations.
Yes.
So you better compare.
Yeah, I wanted to compare to the observed disk radii. I didn't include the radius as a thing we want to match because it's not available for all the disks, and then we will be biased.
Oh, actually, there is a very nice study of lupus, chameleon, and upterscope. All the dust disk radii done homogeneously. And so you can look at that.
Yeah, I should. Yeah, I didn't check it yet. But it's true. I should. I cannot do it with my neural net. You know, I would have to run first the physical model, and then I can really check what's the radii.
Yeah, but I think that's a very strong constraint.
Yeah.
So. Yeah. The other thing I was wondering, I'm really curious about this. What is the efficiency of planet formation? This is your first part of the. What is the efficiency of planet formation in your model? In particular, I'm thinking, what is the average solid mass that goes into the planets and the one that doesn't?
Do you have a number, Alexander?
I was going to say about 1/3.
Yeah, it's
1/3.
quite large. Yeah. But that's if you already have planetesimals.
Only 1/3 goes in the planet. Okay.
That's from planetesimals to the planets.
Yeah.
Okay.
It's not including the dust that goes into planetesimals. This step we didn't model in the first one.
And the embryos are already there.
One
From
third.
planetesimal planets. Yeah.
Okay. All right. Interesting. And if you would include the dust, that would be.
I don't know.
Okay. Just curiosity. Thank you.
Yeah, here I expect to have a number for dust to planetesimals after this project as well, because we have from Christian Lenz and the group in Heidelberg, we have a planetesimal formation model, a parameterized one still. So there it would also give me a planetesimal surface density as the upper.
Okay, another question? Questions all answered? Oh, okay. Gabriel, yeah, there we go.
Yeah, sorry. Hi, Remo. Very nice talk. Just a brief question. Can you comment, or maybe not so brief, or the answer will not be so brief. Can you comment on time zero? So what is your definition of time zero, and does this matter ultimately for comparing to data?
Yeah, it's a good question. I mean, I would say that we don't, well, for us, time zero is when we start a model which does not have infall, right? So it would be the transition between the star and the disk forming, and that's an exact time, then having no infall onto the disk and just evolving the disk. But I know that this is not a sharp boundary. And so in the future, one should really include infall. And then I hope if you also increase the mass of the star, maybe it's really consistent.
Right, because at such small ages, maybe it turns out to matter a bit for, just a few mega year.
Yeah. So it should be, hopefully the timescales are really in our favor, and star formation and the infall process is faster than basically the evolution of the disk. And I think that's more or less what is observed. But, yeah.
Thank you.
Daniel.
Hi, Remo. Very nice talk. I had one question. I don't know if you probably thought about this. Now that you have basically retrieved distributions of properties for disks and evolution, did you consider how the early solar system would map into these distributions? Would it have been a typical disk, typical boundary system in the formation, given what we know about it?
I didn't look into it in detail, but it's certainly interesting to do. I guess what would be really nice is to compare the predicted planetesimal distribution here with the data from basically minimum mass solar nebula. It would be really a good thing.
Yes.
Because, yeah, but I didn't. Yeah, I'm not quite run the forward model or the physical model first.
Okay, thanks.
Hopefully, I can tell you in a year or something.
Okay, is there last call for the question? Okay, otherwise let's thank Remo.